Okay, so changing writing boards or surfaces. The other one was giving problems. So the example next one was limit as x approaches 5. In the numerator, we have the square root. Underneath that radical is x plus 4. Then outside of the radical is minus 3. In the denominator, you have the whole quantity x minus 5. Again, you would start this with direct substitution. You would go in wherever you saw an x, you're going to replace it with a 5. So if we do that, we get the square root of 5 plus 4, and then minus 3 outside, all over 5 minus 5. And so you can see that the denominator goes to 0. I can also see my numerator is going to go to 0 because we have the square root of 4 plus 5, which is the square root of 9 minus 3, all over 0. So 0 over 0. So we want to rationalize the numerator. Okay, so recall that was multiplying. Well, if we rationalize the numerator, we're multiplying this whole function by a fancy one. And that fancy one was the conjugate of the numerator. So that was changing the sign in between that radical on the next term. So instead of having a minus here, we're going to have a plus. So we're going to have the square root of x plus 4. Outside the radical, we'll have a plus and then a 3. We're going to do the same thing to the denominator. So square root of x plus 4. Outside of that radical, plus 3. So again, the point of multiplying by the conjugate is so that we get something in the form of a minus b, a times, or a plus b. And if we distribute that out, that's the same thing as squaring the first term minus squaring the last term. So if we distributed this, we would get the square root of x plus 4, quantity squared, minus, and then 3 quantity squared, all over that denominator of x minus 5, all times the square root of x plus 4 plus 3. So when we were using this trick to find the limit, we did not distribute the piece that didn't have the radical to begin with. Well, if you square something that is a radical, that's going to get rid of that radical, leaving you what is called the radicand, what is underneath. So we have the limit as x is approaching 5 of x plus 4 minus 3 squared, which is 9, all over x minus 5, that quantity times the quantity of square root of x plus 4 outside the radical plus 3 in that quantity. So I'm running out of room, so let's just pull it up here. If I look at combining like terms in the numerator, I have the limit as x is approaching 5. Well, x plus 4 minus 9. Well, positive 4 minus 9 is negative 5, so x minus 5, all times the denominator, this x minus 5. Gosh, I ran out of room. Let's put it in front. And we had the square root of x plus 4 and then plus 3. And we have the limit of this. As x was going to 5. So notice those factors of x minus 5 cancels. So we're left with 1 in the numerator all over, and then we just have that radical x plus 4, and then the plus 3 outside the radical in the denominator. So now we can do the direct substitution. Direct substitution, we get 1 all over the square root of 5 plus 4 outside plus 3. So that's a square root of 9 plus 3 in the denominator. So square root of 9 is 3. So we have 1 over 3 plus 3, which is 1/6.
Professor.
Yeah.
So like in the very first example, you know how like you literally just plugged in the x? Is that because it was like a little problem? Like there wasn't like much to solve and it just directly solved. Oh, I know, never mind, because it wasn't indeterminate, right?
Exactly.
Okay, never
So
mind. Okay, I caught myself.
no, that's perfect. So great point. So Neil hit on a great point. So always start with direct substitution. If a number falls out, like one of the first examples we did, it did fall out. Just gave us a number and it was pretty simple. Then we do it that way. But always start with plugging in the number. And if it gives us that 0 over 0 form, we have to manipulate it, use one of our tricks. And hopefully when we do direct substitution after that, we won't get that form anymore.
Professor, I have a question.
Yeah.
So if we did the first way you showed us with the direct substitution, but we ended up with an actual number, for example, let's say we ended up with like 6 over 0, would we then do the factoring to decide, or would that just already automatically mean it's undetermined and the limit doesn't exist?
Great question, Anna. So if you don't get the indeterminate form when you do that direct substitution, like 0 over 0, you can stop. If you got like 0 over a number other than 0, that is actually 0. Or like you had mentioned, if you get a number over 0, we can't have 0 in the denominator. And since the numerator wasn't 0, so we had like maybe 5 over 0, we would say that actually the limit doesn't exist. It's undefined there. It's okay actually for a limit to be undefined at a value. It might approach some value, but in that case, we'll see actually a little bit later that that's an asymptote, a vertical asymptote. So it's going to, that graph, that limit is actually really shooting off to positive or negative infinity at that value if you get a number over 0.